squiggle lines are false. And some of them are inactive. When they have the funny little white and blue balloons in there, that means that they're fairly recent. And that actually tells you the orientation of the fault itself. So we'll talk about that a little bit more later also. But while we're setting this up, I will go to the next slide. Take the past 5 years, and they're all pretty small. They're all less than 5. The one at Orcas, how many felt the one on Orcas was enough? Yeah. Most people. Good. There are a lot of people. That was 4.5, which is considered a small reduction. But you felt it, and you probably got a little nervous too. Waiting for that tsunami to come along? So these are the general things I'm going to talk about. First of all, we'll talk about definitions. An earthquake is produced by rocks moving past each other, usually in a quick release like that. What happens is the rocks get strained because of compression or tension, and then at some point they can't take it anymore and they break, and that produces earthquake waves. They also happen under volcanoes, and they're very, very handy for monitoring volcanoes and trying to predict when they might blow if they're close. A tsunami, Japanese name for harbor wave, is a catastrophic ocean wave, usually caused by earthquakes, underwater landslides, or a volcano. So I'll talk about all these some more, and then we'll jump in quite soon about plate tectonics. Once we get the mic up and running.
Maybe. I can hear you much better when you're standing up there.
Okay. Can someone advance it? Just push the touchpad here once when I ask for it.
That's it. There's no cable. I'll just put it on my lap and then I won't be standing. No, that's not. Okay.
That's a good way.
Sorry.
So we'll start off with the tide slice through the earth. Bunch of different. To know about plate tectonics, you have to know about the upper crust. There's a continental crust and there's an oceanic crust. That crust, this has what we call vertical exaggeration. The top part is much taller than it should be. In actuality, the thickness of the crust is actually about the thickness of the skin on an apple. And further, all we know about the Earth is in the upper part of the crust. We've never drilled below the crust because there's lots of complications and it's way too far down. So the upper right, the lithosphere is the crust. The asthenosphere below it is part of the upper mantle, and it's actually what we call plastic. It can be deformed. And so the thing about the crust, both oceanic and continental crust, is that it floats and it can move on top of the asthenosphere because of that plastic quality of the asthenosphere. Oh, great. Next slide, please.
On the other direction.
Other way.
Yeah, you're okay.
And just one, please. One more. Excellent.
So that's actually downhill.
So this is looking sideways, looking north if you want, in the Atlantic Ocean. In the middle of the Atlantic Ocean, there's what's called the spreading center. And there's an oceanic plate on the right and on the left. Magma comes up in that spreading center and forces those two plates away from each other. Okay? And this is the simplest model for plate tectonics. It's called a passive margin. There's no what we call subduction or anything like that. And I'll show an animation that really graphically shows this a little bit. Next one. And then we go to an active ocean basin. And there's a lot more to talk about here. Think of this as the Pacific, okay? We're over on the right. There's our Cascade volcanoes going on. It's got an oceanic spreading ridge off the coast. We call our spreading ridge the Juan de Fuca Plate. And it's got a trench. And what that trench does, what that trench is a surface realization of the plate's going this way, it hits the continent, it can't go up the continent, so it actually turns down, we call that subduction. Okay? So that oceanic plate is being subducted. As it comes further down, the earth is hotter as you go deeper. It generates magma, which is liquid rock, and that rises into the crust and it feeds volcanoes. Same sort of thing on the other side, except we don't have a continental margin. What we have, this is oceanic crust, and this is oceanic crust. And so we've got this subduction zone going under oceanic crust, melting rock producing island arcs, like Japan. We've also got what are called hotspots. Yellowstone actually is sitting right over a hotspot, and that's why there's so much volcanic activity, fumaroles and hot springs, those sorts of things. In this case, it makes a volcano, and think of the Hawaiian Islands. Okay, it's exactly what happens in the Hawaiian Islands. Next slide, please. So this is a depiction of the Earth's oceans and continents. We're up there. This is the spreading center down here off South America. You can see the mid-Atlantic spreading center, huge thing, goes all the way up to Iceland and further north, all the way down to Antarctica. And over here you can see Japan and a bunch of other types of island arcs. Now, this is Hawaii right here. The hotspot is stable, it doesn't move. What happens is the plates move around on top of the hotspot. So we can see that that's the big island. You go to the northwest, you get the smaller islands to the northwest. And then you go further up and you see what are called seamounts. They're submarine volcanoes that are going almost north-south. We can take this picture and use it to figure out the way that the Pacific plate has moved through the years. Okay? So the Pacific plate right now is moving that way. And it used to be moving that way. Can you picture that in your mind? And up on the upper right, the green are all subduction zones, and the red are all spreading centers. And that's very generalized because there are some areas that have a lot more complexity. Next, please. There are about a dozen major tectonic plates in the world. Next one. And here is a good graphic representation of what we call the Pacific Ocean, the Ring of Fire. Okay? All the colored things are subduction zones. And whenever you've got a subduction zone, almost in every single case, you've got a volcano. And thus, you've got fire. Now, while we're on this one, Pacific, but also Mediterranean, has a lot of tectonic activity. Plates moving around, subducting, earthquakes, volcanoes. We're going to be talking about tsunamis in a bit. In 365 AD on Crete, there was a massive volcano. Wiped out pretty much the whole Minoan civilization. Made its way all the way over to Egypt and all through the northern and eastern Mediterranean and wiped out who knows how many people and structures and those sorts of things. So big earthquakes especially in a confined area like the Mediterranean, can do a lot of damage. Actually, there were boats, merchant marine vessels, that were swept 2 miles onto land during that tsunami. Another little depiction of the subduction zone on the board right there. In the upper right, you can see all those red things, the volcanoes. That's why we call it the Ring of Fire. Next one, please. Okay, I'm going to have to operate this. 200 million years ago, all the continents on Earth were lumped together. And there's a great story behind that, but we don't have all that. So I will, can you just stay there? That's great. I can just look over your shoulder. So I'm going to, hopefully, no,
What did it pass it?
didn't work right off the bat. So about 300 or 200 million years ago, a little bit less, see North and South America and that star, that's when the Atlantic started to form. Eurasia and North America were right next to each other before that. But 140 million years ago, I'm going to show the whole of the bat. 100 million years, you'll see that North America is, the Atlantic Ocean is much wider, sequentially in all these pictures. An interesting thing is that during what we call the Cretaceous period, about 100 million minus years ago, there was a giant inland sea, and persisted for many millions of years, and that's where we have a good number of our coal deposits, because it was a much warmer climate at the time, and animals, and especially plants, grew in abundance and got buried in mid coal. Next one, please. Okay, about 140 million years ago, look at our west coast. I don't have a pointer, but you can see that big, oh, I got a finger. You can see that big embayment right there. It's just basically a hole in western North America. And all of those brown blobs are island arcs that started assembling off the coast here. There's some down in the south here also that also made their way up from Baja area to our area, which is a little mind-blowing. And the next one, please. We'll talk a little bit more about that aggregation in a minute. This is what's called a geologic map, and it's very colorful in different colors, denote different rock types. The bright colors on the right-hand side are completely different from this whole area here, which has the same types of colors, and same with that. There's a big, big fault called the Straight Creek Fault, just east of Mount Baker. Mount Baker is up here, and you see that blue blob right there? That's called the Twin Sisters. And 2 slides from now, we'll talk about that a little bit more. The next slide, look at the Olympic Peninsula, okay? The next slide will show you, tectonically, why that's there. There was an offshore volcano edifice, a very large one, on the top right, top left, 30 to 50 million years ago. And it was being pulled in along the oceanic plate until it hit the continent. Now, usually what happens is that it subducts and goes underneath the continent, causes volcanoes and all that stuff. This thing was so big, look at the middle one there, that it actually stuck in what we call the accretionary wedge, which is a lot of sediment coming off the continent and into the ocean. And then a little bit later, that got, you got pressure continuously coming in from the ocean plate. And that got tipped all the way vertical. And so most of what we see on the peninsula is a remnant of that old, very large volcano that was on the coast, which I think is pretty. And it's like these. This is another geologic map of San Juan Islands. And look, Weymouth Island is on it. A lot of people think that the San Juan Islands end at Rosario Strait. That's not true. They're all connected. We call this type of map a map of terrains. And I know it's spelled funny, but a terrain is a group of rocks that share similar characteristics, age, rock type, those sorts of things. So here we have what's called the Fidalgo terrain, and there are several others up there. Draw your attention to the dark, mostly dashed lines. Those are what we call suture zones. Think of them as old faults. Most of them are well annealed, they're not moving at all. But they are the things that kind of hold those things together. And each of those terrains was one of those island arcs that we showed off the coast 2 slides back. What else was I going to say? Oh, and the ages. You got to pay close attention to the ages of rocks also if you're a geologist, because they help you figure out the whole history of the area. Fidalgo Island rocks, the youngest are about 100 million years ago, which is quite early. Turtleback Mountain up there is 450 million years ago. So I can stand on Mount Erie near my house on Fidalgo Island, and standing on 150 million year old rocks and look across and see 450 million year old rocks. A lot of variety there. Next one, please. This just takes basically what we were seeing in a bat view and envisioning a slice through the crust. Okay? What I want you to see here is that these are San Juan Islands, and now we're up into Mount Baker and the North Cascades up here. They're all the same terrain. They're all related. CH, that's all one terrain, that's all another terrain. So all of these island arcs that came in were big, because this is about 70 miles from the islands out to Mount Baker. I also want to draw your attention to that, which was a blue blob on the earlier one. That's the Twin Sisters Range. Some of you might be familiar with that. Next slide, please. And that's what it looks like. And the cool thing about that is, we talked about mantle rocks a little bit. Twin Sisters is all mantle rock, but somehow got thrust up, way up onto the continent. It's about 9 miles from Mount Baker. It's not as tall as Mount Baker. I think it's 8,000 feet, something like that. But it's big. But it's also the largest single mass of mantle rock on the face of the earth. So that's pretty good. Next one, please. That just kind of shows another cross section. Next one. Little bit about glaciology, because it shaped everything in Northwest Washington especially. This happened from 2 million years ago until the climate, and there were about 7 different evolutions of warmer, colder, warmer, colder. So there were 5 or 6, 7 glacial periods where glaciers came down. Next one. So about 14,000 years ago, this is what our inland sea looked like. You all know Puget Sound, A big lobe of ice cap went through the Strait of Fuca. See Valve Island there, buried in a mile of ice. Next one. During an ice age, the ocean elevation goes down because all the water, a lot of the water on the earth is being stored in glaciers up in the mountains. And then when glaciers melt, water comes up. Glaciers do a lot of damage to the surface of the earth. They pluck out rocks from the mountains, bring them down. As they come down, the rocks are grinding, making silt and sand and all sorts of things. And they dump them out, like in South Puget Sound, and also around here, because glaciers also retreat when it warms up. And they just go back up in the mountains and eventually all melt away. Next one. I just wanted to show an active glacier. That was up in southwest Alaska this summer. And, that was something to see. That's pretty amazing. That's 4,000, a little bit less than a mile wide. And all the glaciers, all over the world are retreating. Most of you are probably heard that. And I could say, due to human cause, global warming. Next one, please. So this is again from Mount Erie up to Hidalgo, and it's looking out to San Juan's to the west, northwest. All of these were really rocky mountains before the Ice Age. And one of the many things that glaciers do is strip the landscape of soil, any big jutting rocks, it'll rip those off and get incorporated into the ice. And like I said, it's about a mile thick over this area. Next one. And when glaciers go through, like I said, they've got obviously ice, but rocks of various sizes, and sand, gravel, and those are at the base, and they make striations on the rock. And you can see that whenever you get higher up in the mountains around here, in the mountains especially. In the bottom there, 150 tons per square foot at its base. It's a lot of ice. Next one, please. There's just one example of a big erratic. An erratic is a bigger boulder that's carried in the ice. This one is actually from Lummi Island area, so it didn't get transported very far. I'm sure you see all over the place granite-type boulders that are mostly rounded, that are deposited all through here. They all came from Canada, and sometimes quite far north in Canada. Next one, please. Anybody been there? Yeah. Washington Park, northwest part of Hidalgo Island. There's still a little bit of controversy about how that big groove was made, but I'm convinced that there was a large erratic that was down in this valley and got along the side of this cliff and just carved this big groove in there. If you look at it closely, you can see the striations. You don't have to look at it closely, but in some places it's still like highly polished rock because the sand and silt were also in that ice and polished it off to not quite a mirror finish, but pretty close. And the next one. Okay, glaciers melted several times. The last one was about 12,000 years ago, and when glaciers melt, as I mentioned, or when they form, they take up water from the ocean. When they melt, that water goes back in the ocean. So what we have here is what this area looked like about 10,000 years ago. And it's all marshy. That's partly because there's more water in the ocean, but it's also partly because when the glacier is sitting on top of the crust, it actually depresses the crust. So this asthenosphere that is plastic. It can kind of squish down and around big things, and so the surface actually, in some places, 800 feet it's been depressed. It actually rebounds pretty quickly. But in this area, we think maybe 400 feet of sinking happened during the last glacial episode. And the next one shows wave cut terraces. Okay, what are those like? Well, when the glaciers left, the ocean was happy because they could make waves and all sorts of things. And they started, each one, they started making a bench there, just eroding the bench. This is all sedimentary stuff, so it's pretty easy to erode. Okay, and then what happened? Well, after a time, there was an uplift of this area. And it was probably a pretty dramatic uplift because, like a fault, like I said, get your strain, and it can't take it anymore, and then it comes. And so the whole landmass comes up, and beach 2 is made, and the current beach in this scenario is made also. If you want to see a really good example of this, go to Farmer Market Road between Highway 20 and Edison, and I recommend, there's a big slope there. I recommend going south, so you're going up it. You'll go up it, and then it'll go like that. And then you'll go up it again, and then go like that. I counted 6, maybe 7 different old beaches going up there. It's pretty cool. If you go really fast, then you're The next one, please. This is what's called a LiDAR image. A light, distant, and ranging, kind of like radar, except it uses a different wavelength. It uses a laser light. And this is a topographic surface with all the trees stripped out. The nice thing about a laser is that it can get between trees and actually map the real ground. Because in the forest, all you see is the treetops. And so it can actually strip everything off. And each one of these is an old beach. I counted 7 or 8 in there. Sorry, this is the one part of Lake Island, just across the street. And there's the airstrip. And obvious. Okay. What will the next one bring? I gotta keep going. Let's get through the glacial deposits. We've all seen bluffs and things like that. Pretty amazing. Let me jump forward here to 4 slides. Got erosion. This is interesting. Some of the bluffs, especially on the western part of Whidbey Island, are eroding at over 1 foot a year. So, okay, a little bit about climate change, because we're all living it. 2 pictures, one from 2012 and one from 12 years after. They get a lot of storms at Swantown, which is west of Oak Harbor, and they're pretty severe and they damage houses and everything, but they seem to be getting worse. There's variability in weather all the time, but just look at the one from last year. Huge logs coming up off the beach, completely inundating the road. Ocean level rise, of course, which is happening because of several things. First of all, warm glaciers are melting. Second of all, water expands when it heats, and we all know the oceans are getting warmer. Next one, please. This is just the last 30 or so years of ocean surface elevation rise. And just in 2024, it went up a 1/4 inch. And that doesn't sound like a lot, but in 4 years, it goes up a whole inch. Okay? In 40 years, it goes up 10 inches. So, it's a thing. Next one, please. I got another one or two graphs of this. Since 1900, ocean's risen 9 inches. You see here about where industry, really, the industrial age really started, lots of coal burning, etc. And I think I've got one more. So, current rate suggests that by 2050 or so, the ocean around here will be about 2 feet higher. These are all models that were done, I'm not sure when, maybe 10 years ago. Obviously, these lower models are kaput now because they're way out of bounds. And I think we're looking at probably that model or that model, depending on a lot of factors. If we do something about controlling our CO2 emissions. Next one, please. Next one, down. Sorry. So, with 2 feet of ocean rising, which might happen in just 25 years, these areas, there's claims up there, this is Connor, these areas will be basically swamps. If the current projections hold true. Okay, let's get on to some maturity things here. How about tsunamis? Next one, please. Yes, ma'am.
What is that, the rise and the melting of the glaciers, which are fresh water, due to the salinity of the
Salinity is less, yes.
above and
So go over faults real quick. There's strike slip faulting, that's like the San Andreas fault. They just go like that. And we have reverse thrusting and normal faulting. Next one. Okay. Here's kind of a mega picture of the Northwest. Where is, repeat the sound of Seattle. Okay. The Seattle Fault is on here. I think it's on the next one. Okay, go back up, sorry. So anyway, these are major faults through the Northwest. The one on the right has some of the smaller ones. Right in the top there, you see DNF. That's called the Darrington Devil's Mountain Fault. And I live on the south side of Fidalgo, and that's about 4 or 5 miles away from me. And that's a fault that the U.S. Geological Survey says has the very real potential of generating a 6.5 earthquake, which is pretty large, especially if you live there. Next one, we're going to have to wrap up pretty soon. That Darrington Devil's Mountain Fault. This is Devil's Mountain south of Mount Vernon. It's hard to pick out from the freeway. This is another line item, so you see real representation. This is the fault. It's a deep valley. It goes right through the mountain. And it's active. So we will certainly get some rumblings out of it at some point. Like many things in geology, it's difficult, if not impossible, to predict earthquakes, just like it's hard to predict volcanoes. Next, please. Okay, here's the one I showed earlier. The star is Volga. And the state of Washington, Northwest Pacific Seismic Network, Pacific Northwest Seismic Network, says that that was on a new fault that hadn't been mapped previously. But this red line right here looks like it's pretty darn close. So anyway, whenever you see these cool baseballs with funny colors, those were fairly recent, and they just tell you the orientation of the fault, whether it was a strike slip or first fall understand the tectonics of the area. Next one, please. Okay, now we go to the big quickest island fault here. And the map up there shows where it is. It's a big basketball there. And the interesting thing that the Pacific Northwest Seismic Network saw was a whole bunch of very small aftershocks. And that's not typical. And they don't explain why it's atypical, but it's just something that's adding more information into the whole picture of earthquakes in Northwest Washington. Yeah, it's not associated with previously known active faults. Next one, please. Okay, I'm going to sit right toward the end. Because we're out of time. You already know that stuff. Okay. Frankly, I don't know a lot about tsunamis, but I looked into it some. We talked earlier about volcanic eruption, submarine earthquake, landslide. The big one is a meteorite strike. And GICCA is the one that wiped out the dinosaurs during the Cretaceous, Triassic. Cretaceous Tertiary extinctions. So let's not worry about that, okay? I mean, get some sleep tonight. The odds of that are just astronomical. Next one, please. Tsunamis are interesting in that when they're generated, they don't show really any expression on the surface because they're really, really long wavelengths, miles long. So they go like that. Okay? But when they get closer to land and the shoreline shallows, then they start getting angry and they rise up. And they can do the biggest, one of the biggest, latest ones was the one in Japan, it's 10 years ago or so. But they happen fairly frequently. Oh, the big one down in the South Pacific was interesting. Next one, please. There's a graphic that works. So the shore shallows abruptly often, and the peaks become much higher. And then they come up into land, and they crest, and it's just a huge wave that can do a lot of damage. And the next one, okay, I sure hope this works. It doesn't.
Maybe we don't want to see those.
Well, afterwards, it's showing on my screen here. So afterwards, if you want to see them, I can do that, but I don't know how to project them.
Can you just correct it? Terrifying.
Okay, I think that we're pretty good on time, so we've got time for questions. The short answer for that simulation is the interior sailor seat, hold that over please, wouldn't be nearly as affected as the coast, because tsunami's coming right in the coast. To get to here, it's got to negotiate Strait 1 Fuga. It's got to go up Rosario Strait. It's got to thread through the islands. And so several feet is very possible, but not 9 or 10 or 12, like a lot of tsunamis generally.
I just got through reading a book, it's called, Huge Earthquakes, 9 point something and above megaquakes. And it talked a lot about the Cascadian subductive zone specifically. It was put out in 2011, 2012. They were saying, and they said in the book, that we would have approximately an hour and a half from the time of the quake, and I'm talking about the huge one that's going to drop all of the coastline 5 feet, because that's what they say. And it goes from somewhere up by British Columbia all the way down to Mendocino, California. They say that we would have about an hour and a half's notice to the to the northerly portions of Puget Sound. And I want to know what they're calling the northerly portion of Puget Sound. Is that like the North Bainbridge Island, or are we talking Orcas Island? Because I need to know how much time I've got to try and get to a high spot. And they were talking, they said that in the book they also mentioned that it's going to be approximately, if it was anything like the last one in 1700, that it would be approximately a 30-foot wave, 30-foot tidal wave. And I know that there are several waves that get generated off of a tidal wave. The 30 feet is an awful lot of water.
It is, and again, that would be at the coast, that wouldn't be in one of the tanks.
Right, I know it's got to navigate through the 301. If you could hit Bellingham and then, spread south from there. But mostly my question is about time.
Yeah, time is obviously very, very important. One of those simulations has an earthquake happening right at the western part of the Strait of Montgomery. And it comes in